Hi everyone, this is Dr. J. Ravindranath Reddy, Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So here we are discussing the numerical methods and integral transform course. In that course, we are taken the concept of Laplace transform. So in this Laplace transform, you are going to discuss first shifting theorem and second shifting theorem. So in this video, we are going to discuss first shifting theorem and second shifting theorem here. First, we will concentrate on the first shifting, and then we will take some problems on the first shifting theorem. Then we will go for the second shifting theorem. So here, in this, we are going to discuss first and second shifting theorem of a Laplace transform. So first, we will take the first shifting theorem here. So let us take the statement of first shifting theorem in the Laplace transform. So here, L of f of t is equal to f bar of s. Then Laplace transform of e power at into f of t is equal to f bar of s minus a. So f bar of s minus a. So this is the first shifting theorem here. If L of f of t equal to f bar of s, that means Laplace transform of f of t, if you consider that value as f bar of s, then if any function f of t is multiplied with some exponential function e power at, then if you want to find out the Laplace transform of such type of functions, then this value is equal to f bar of s minus a. Now let us prove this condition here. So by definition, we have the Laplace transform definition. Now take that definition here. So L of f of t is equal to integral 0 to infinity e power minus st into f of t dt. So this is the Laplace transform definition here. So now here in Laplace transform we have taken a function f of t. So on the RHS side, in the inside the integral, we have taken the function f of t as it is. Now we are going to apply the Laplace transform for this function e power at into f of t. So Laplace transform of e power at into f of t is equal to integral 0 to infinity e power minus st into, now take this function, entire function e power at into f of t here. Now once if you observe this function, exponential functions inside this integration, so we are having two exponential function e power minus st into e power at. So bases are equal, so add the powers. So if you add the powers, you will get this value is equal to integral 0 to infinity e power minus st plus at into f of t dt. Now from this you take minus common along with t. So if you take minus common here, you will get integral 0 to infinity e power minus of s minus a into t f of t dt. So now while you are taking the definition of Laplace transform, so we have taken L of f of t is equal to f bar of s here. So since here in the power of this exponential function the coefficient of t is s, so we will get this integral value in terms of s. Now here if you compare this integration with this standard integration, so here in place of s we are having s minus a. If you have s here, this entire integral value we can consider as f bar of s. Now in place of s here we are having s minus a, so we will consider this entire integral as f bar of s minus a. Or we can apply the substitution method, put u is equal to s minus a, and we can take f of u, that is s minus a. Okay, so this is the first shifting theorem. So suppose if any function f of t is multiplied with some exponential function e power at or e power minus at, then for this entire function, if you want to find out the Laplace transform, then we have to take the help of this first shifting theorem. That is the main important of first shifting theorem. And similarly, so here f of t is multiplied with the exponential function whose power is a positive power. Suppose if you have the Laplace transform f of t is multiplied with e power minus at, Then if you want to find out the Laplace transform for this entire function, we can follow the same procedure. So here you will get f bar of s. Suppose if you have a positive power for this exponential function, here we will keep s minus a. If you have a negative power for the exponential function, then in the function f bar we have to keep s plus a. If you have negative power, here we have to keep positive power. If you have positive power, here we have to keep negative sign here. That is the second one. So note, by using above property, we have Laplace transform of e power minus at into f of t. So this we can write it as f bar of s plus a. So even in both cases we can use first shifting theorem. So whenever f of t is multiplied with exponential function whose power is positive or whose power is negative, in both cases we can go for the first shifting theorem and we can find out our required Laplace transform for the given function. Now for this is first shifting theorem, we are having some more applications here. So we'll see what are the applications of this property here. So here in the previous videos we have seen Laplace transform of t power n is equal to n factorial by s power n plus 1. So whenever this t power n is multiplied with some exponential function, for example, if you consider this t power n is multiplied with e power at. So now, whenever we are having these type of functions, we can apply this first shifting theorem. By using this first shifting theorem, we can get this value here, n factorial by s minus a. So here we are having a positive power for this exponential function. So we have to keep s minus a whole to the power of n plus 1. So we'll see how to find out. So we have seen Laplace transform of e power at into f of t. So here if you want to find out this, from this it is very clear that this value is equal to f bar of s minus a. So how can you get this f bar of s minus a here? So before going to find out that f bar of s minus a value, first we will find out f bar of s value. And after finding this f bar of s, if you compare this, in place of s here we are having s minus a. So whatever the value we got in f bar of s, replace that value with s minus a, s with s minus a. That is the meaning of f bar of s minus a. This is the way how we can get this f bar of s minus a value here. So here, how can you get this f bar of s here? Now you identify the value of f of t. And for that f of t, you apply the Laplace transform. So we know that L of f of t is equal to f bar of s. After finding this, you just replace s with s minus a, because here we are having a positive power, so we have to keep negative sign here. And similarly, vice versa, reverse. If you have negative power, then here we have to keep positive sign. So here find out Laplace transform of f of t, and in that replace s with s plus a. Then we can get our required values here. So based on this concept, these are the applications we have seen. So next, sin bt. This sin bt is multiplied with the exponential function e power at. So whenever we want to find out a Laplace transform for this, then we have to take the help of this first shifting theorem. So first shifting theorem says that first find out the Laplace transform of sin bt. Neglect this exponential function and consider the remaining function, and then find out the Laplace transform. You will get that Laplace transform of that f of t. So Laplace transform of sin bt is equal to b by s square plus b square. Now what we have to do in this, we have to replace s with s minus a, because we are having a positive power. So if you replace s with s minus a, you will get Laplace transform of this entire function here. Okay, so like this, we are having the many applications of this. Similarly, e power at into cos bt. If you want to find out the Laplace transform for this entire function, first you find out the Laplace transform of this f of t. You will get that value s by s square plus b square, and in that replace s with s minus a. We will get this Laplace transform of this entire function here. So if you replace s with s minus a in the numerator, you will get s minus a by s minus a whole square plus b square. So like this, whatever the formulas we have seen, whatever the Laplace transform values we have seen for the elementary functions in the previous video, for all that formulas we can multiply, for all that functions we can multiply this exponential function e power at as well as e power minus at, and you will get new formulas here. Next, sin hbt, follow the same procedure. So then sin hbt, this is our Laplace transform of sin hbt. Then multiply that sin hbt with the exponential function e power at. So replace s with s minus a. And similarly cos hbt. Okay, so like this, whatever the elementary functions we have seen in the previous video, for all that elementary functions, if you multiply with the exponential function e power at or e power minus at, then you will get a new formulas using that first shifting theorem. So this we can consider as the applications of this first shifting theorem here. Now let us take one example for this first shifting theorem, and we will see how to find out that Laplace transform of that given function. So this is the function he has given, e power at into cos 2t. So for this exponential function, for this finite function, we have to find out the Laplace transform here. So already we said that in the previous slide, we said that whenever some function is multiplied with exponential function, then neglect that exponential function, neglect this exponential function. First you concentrate on the remaining function cos 2t, and for this you apply the Laplace transform. You will get that value in terms of s. Then replace s with, so here we are having a negative power, you compare that with e power minus at. So this is equivalent to e power t. This can be written as e power minus 1 and 2 t. Now in place of a, here we are having 1. So replace s negative power, so keep positive. A, in place of a, here you will get a is equal to 1. So then we can complete our problem here. So by using this technique, using this first shifting theorem, we can find out the Laplace transform of this entire function. So follow the procedure. So already we said that first find out the Laplace transform of cos 2t. We know that s by s square plus 2 square. This is the formula. So we are having the formula Laplace transform of this cos at is equal to s by s square plus a square. So replace a with the 2. You will get s by s square plus a square. Now we don't want this Laplace transform of cos 2t, but in our problem we want cos 2t is multiplied with exponential function. For this entire function we have to find out the Laplace transform here. So once if you observe this entire function, this is of the form e power minus at into f of t. So for this we have to apply the Laplace transform. So whenever we are having this type of functions, then we can take the help of this first shifting theorem here. So first take the first shifting theorem. Laplace transform of e power minus at into f of t is equal to, since here we are having a negative power, so inside the brackets we have taken a positive sign. So f bar of s plus a. So how can you get this f bar of s plus a? First find out the value of f bar of s, and then in that replace s with s minus a, then this value is equal to f bar of s plus a. So now f bar of s, how can you get this f bar of s here? By applying the Laplace transform here. So by applying this f bar of s, we know that Laplace transform of f of t is equal to f bar of s. So I have replaced that f bar of s with the Laplace transform of f of t. So replace s with s plus a. Now apply the same procedure for the given problem. So Laplace transform of e power minus t into cos 2t. For first you concentrate on this function. For this function you apply the Laplace transform. So Laplace transform of cos 2t, already we got this value. Cos 2t is equal to s by s square plus 2 square. Since here the power of this exponential function is a negative sign, so we have to replace s with s plus. Now we have to get the value of a. So minus t can be written as minus 1 into t. This is of the form minus a into t. In place of a, here we are having 1. So replace s with s plus 1. So this is our required value here. So this is a simple point here. So whenever any function f of t is multiplied with some other exponential function, then if you want to find out the Laplace transform of that entire function, this type of functions, then we can use the concept of first shifting theorem. That is the important point we have to remember. Now let us take one more example here for the first shifting theorem. So this is the function he has given, t cube into e power minus 3t, whatever it may be the order, a into b or b into a. So first rearrange this, you will get e power minus 3t into t cube. Now this is of the form e power minus at into f of t. Now from this you get the value of f of t. F of t is equal to t cube. Okay, because t cube is multiplied with some other function. If any function multiplied with exponential function, then that function we have to consider as f of t. So like this, you analyze this and get the value of f of t. Then apply the Laplace transform for f of t. You will get f bar of s, and then replace s with s plus a. It's because minus sign. So here f of t, Laplace transform of t cube is equal to 3 factorial by s power. So we have the formula. So Laplace transform of t power n is equal to n factorial by s power n plus 1. So here n is equal to 3, which is a positive integer. So we can take this factorial formula here to find out this Laplace transform. So 3 factorial by s power 3 plus 1. So if we simplify this, you will get 6 by s power 4. This we can consider this value as f bar of s. Okay, now you consider this entire function here. So by using this first shifting theorem, why you are using this first shifting theorem? Because this t cube is multiplied with exponential function. So whenever any function is multiplied with exponential function, then if you want to find out the Laplace transform for the entire function, then we can take the help of this first shifting theorem. That is the use of this first shifting theorem here. So we have the formula. So since here the power of this exponential function is a negative power, so we have taken that standard formula whose exponential function power is negative sign. So e power minus at into f of t, Laplace transform is given by f bar of s plus a. So now this already we have seen. How can you get this f bar of s plus a? First find out that f bar of s and then replace that s with s plus a. We will get over this. How can you get this f bar of s here? By applying the Laplace transform for f of t. How can you get this f of t here? Neglect this exponential function, and whatever the function is remaining in the given problem, you consider that function as f of t. That is the procedure we have to remember. Okay, so now this is equal to, so here our f of t is t cube. So Laplace transform of t cube. So we got this value, replace s with s plus a. Now compare this, in place of a here we are having 3, so we can replace a with 3 here. Now we got this Laplace transform of t cube here, replace that value 6 by s power 4 and then replace s with s plus 3. So finally we will get our 6 by s plus 3 whole to the power of 4. This is the Laplace transform of e power minus 3t into t cube. So this is the way how we can use this first shifting theorem, and how to get this Laplace transform for any function which is multiplied with exponential function. Okay, so this is about the first shifting theorem, how we can apply this first shifting theorem for the given functions to find out the Laplace transform. Now we will go for the second shifting theorem here. So the second shifting theorem, so this is, or we can call it as a second translation, or we can say that the second shifting theorem. Now let us take the statement of this second shifting theorem or second translation. So as usual, L of f of t is equal to f bar of s. Okay, now he has given some function g of t, for which we are going to find out the Laplace transform. So now whenever this g of t is defined in this standard form, that is g of t is equal to f of t minus a. We can consider that g of t value as f of t minus a whenever the t value is greater than a. Otherwise, we can consider this g of t value is equal to 0 when our t value is less than a. So, whenever the given function is mentioned in this standard form, then if you want to find out the Laplace transform for this function, then we can take the help of second shifting theorem. So, Laplace transform of g of t is equal to e power minus as into f bar of s. So, when we can apply this first second shifting theorem here, whenever this g of t is, whenever the given function is in this standard form, then if you want to find out the Laplace transform for this g of t, then we can go for the second shifting theorem here. Next, we have another form of second shifting theorem here. Let us see what is the standard function we are going to get in this second form. So, same L of f of t is equal to f bar of s. And now, whenever the function is in this form, Laplace transform of f of t minus a into h of t minus a. Whenever this is multiplied with a unit step function, then we can also use this second shifting theorem here. So in both cases, we can use this second shifting theorem. So now we'll take one example for both forms. So for this we'll take one example, and for this we will take another example. Now we'll see how to find out this Laplace transform of g of t whenever it is defined like this. So here h of t minus a, here we are having h of t minus a or u of t minus a, we can define this. This is a unit step function, or Heaviside unit step function also we can call it, at t is at the point a. Now take this problem, g of t, find the Laplace transform of g of t where g of t is defined like this. So now whenever we get this type of functions, immediately we have to remember the second shifting theorem here. So why? Because our g of t is in this standard form. So what is our standard form here? G of t is equal to, just now we have seen, integral f of t minus a when t value is greater than a and is equal to 0 when t value is less than a. So here f is some function, it is in terms of t minus a. So in place of that function, here we got a trigonometric function cos, and it is of the form t minus pi by 3. Some a is some other point. So you compare this. So by seeing this function, we can remember our standard function of g of t, which is we discussed in the second shifting theorem. So now you compare this, get the value of f of t. So here you will get f of t minus a. So here in place of f of t minus a, here we are having t minus pi by 3. So in place of s, we are having a trigonometric function cos, and in t minus a, we are having t minus pi by 3. So by comparing this, you will get a is equal to pi by 3. So now we know the value of f of t minus a or t minus pi by 3. Now from this I want to get the value of f of t. Just replace t minus a with t, you will get our cos t. So Laplace transform of f of t is equal to Laplace transform of cos t is equal to s by s square plus 1. This is our f bar of s. Okay, comparing the function standard g of t with the standard function and getting the value of f of t minus a. From that f of t minus a, we have to get the value of f of t. Once after finding that f of t, we have to get our Laplace transform. Why you are using this one? We have the formula. So here we have seen f bar of s, f bar of s. Here also we are having f bar of s. How can you get this f bar of s here? So in order to get this value of f bar of s, first we have to get the value of f of t, and then we have to find out the Laplace transform here. So once if you know the value of f of t, then we can apply the Laplace transform. After applying, you will get a function which is f bar of s, because in the formula we want f bar of s. Because of that reason we are getting the value of f of t. So now we got the value of f of t, update the Laplace transform, we got the f bar of s value here. Now we are ready to apply that second shifting theorem. So what is our formula here for the second shifting theorem? So what is the formula? This is our formula. Laplace transform of g of t is equal to e power minus as into f bar of s. So here a is equal to pi by 3. Okay. So e power minus cube minus a. What is the value of a here? Pi by 3 into s into f bar of s. What is our f bar of s here? S by s square plus 1. Now simplify this. S into e power minus pi s by 3 by the denominator s square plus 1. So once if you remember this second shifting formula, within seconds we are going to get this Laplace transform for this type of functions here. Okay, so very simple. We can complete this. You can use this second shifting theorem and we can get our required Laplace transform value. Now let us take one example here, which belongs to the method form 2. We have taken two forms for the second shifting theorem. One is whenever that g of t is defined with f of t minus a, that is one form, and whenever that function is in the form of h minus a, h of t minus a into, so we have seen this form f of t minus a into h of t minus a. Whenever we want to find out the Laplace transform for this type of functions, we are going for the second form of second shifting theorem, that is another form. So now whatever the function he has given, you compare that function with our standard function f of t minus a into u of t minus a, or we can take h of t minus a. Both are same. Now here you compare this and get the value of a. So we can take a is equal to 2. Now for each and every problem, first we have to get the value of f of t. Then you apply the Laplace transform for f of t. We can get our f bar of s. Then you can substitute that f bar of s in the standard formula. Then we can complete our problem. So now here we got a is equal to 2. Now I want to get the value of f of t here. How can you get the value of f of t? You take the standard form f of t minus a. Whatever the function is multiplied with u of t minus a, you consider that function as f of t minus a. So here you will get f of t minus a is equal to t minus 2 into whole cube. Now here a is equal to 2, that is f of t minus 2 is equal to t minus 2 whole cube. Now replace that t minus 2 with t minus 2 with t. If you replace this, you will get t cube. So that's why we have taken f of t is equal to t cube. Now immediately once after getting that f of t value, then apply the Laplace transform for that f of t. You will get our f bar of s value here. Now we are ready. Once after finding that f bar of s, then we are ready to apply the second shifting theorem here. So now by using the second shifting theorem, first write down the formula. Laplace transform of f of t minus a into h of t minus a is equal to e power minus as into f bar of s. Now here we got f bar of s value, we got a value. Now just replace that values here. So t minus 2 whole cube into h or u t minus 2 is equal to e power minus a. We got that a value is equal to 2 into s e power as. Replace a with 2 here, you will get e power 2s, and f bar of s, we will get that value is equal to 6 by s power 4. So you will get, multiply this, you will get 6 into e power minus 2s by s power 4. This is the way. Use the formula, substitute the value of f bar of s into a in that standard formula, then we can get our required Laplace transform value. Now This is we have another problem here, e power minus 3t into u of t minus 2. So here this is not in our standard form. What is our standard form here? F of t minus a into u of t minus a. This is our standard form. Now you compare these two and get the value of a. So here we can take a is equal to 2. So our standard form is t minus 2 into u of t minus 2. So we don't have any problem with this. And whatever the function you are having here, this is not in the form of t minus 2. So it is only in terms of t, because here in the power in the numerator, in the power of that exponential function we are having t. So now our task is we have to convert that e power minus 3t into this standard form, f of t minus 2. Then only we can apply this second shifting theorem here. Now we'll see how to apply this, how to convert this. So we have compared that f of t minus a. So now this is our problem. So now our task is I want to convert this entire function into this standard form. So here in the function, wherever we are having t, replace that t with t minus 2. And then simplify this, you will get e power minus 3t into e power 6. Okay, but in our problem we got only e power minus 3t. We don't want this e power 6 here. Now I want to remove this e power 6 here. How can you remove this? By multiplying with e power minus x. Now use this e power minus 6. So into e power minus 6. So we can cancel this with that e power 0. You will get this value is equal to 1. Once again you will get this one. So in this problem what we are doing is, if the function is not in this standard form f of t minus a, that is our standard form. If it is not in the standard form in the given function in the problem, then our task is we have to convert this e power minus 3t into the form of t minus 2. Okay, suppose if we get any extra terms, then we can convert that extra term into 1. So that extra term here we will get e power 6. So I want to remove that e power 6. So I have multiplied that e power 6 with e power minus 6. Bases are equal. So if you add the powers, you will get e power 0. E power 0 is 1. There is no problem with that. Now we are ready to apply this e power 6 minus 6 you take out. Next, this is our function. Now e power minus 6 is a constant, so no need to worry about this constant. Now you concentrate on this entire function, and now that entire function is in the form of f of t minus a into u of t minus a. Now compare this and get the values here. So now both sides you apply the Laplace transform. So e power minus 6 is a constant, so we can take that constant outside this Laplace transform. Now this is our standard form. So here you compare this and get the value of f of t e power minus 3t. Then apply the Laplace transform, we will get our f bar of s value here. Now we are ready to apply the second shifting theorem. So that is, so e power minus as into f bar of s. So e power minus 6, that is a constant here. And now in place of this, use that formula e power minus a. What is our a here? 2. So e power minus 2s into f bar of s. This is our f bar of s. Replace this. We can get our required Laplace transform for the given function using the second shifting theorem. So in this video we have seen when we can apply this first shifting theorem, what is the use of first shifting theorem and second shifting theorem of a Laplace transform, with some examples here. In the next video we will discuss what is change of scale property, when we will apply this change of scale property in the Laplace transform for the given function. Thank you.